In today's lesson, we're going to continue talking about temperature and heat. We learned last time that heat flows due to a difference in temperature, and that temperature is a characteristic of an object, and heat is an energy, and the energy of the moving of the particles, or the energy that radiates between the two objects. Today we're going to learn about temperature. We're going to learn the different temperature scales, and heat, we're going to learn about how it's transferred between objects or anywhere. Now, if we're talking about how heat is transferred, how easily it is transferred, or how much heat is transferred, we have the equation here, Q equals mc delta T. Q is the amount of heat. So the amount of heat that's going to be transferred depends on m, c, and delta T. M is the mass of the object. So the mass of the object, how big it is, the size of the object is going to determine how much heat flows. So if you think about it in terms of a pot of water on the stove, if you have a very small pot, you can get the heat from the stove into the water very quickly and get it to boil. If you have a big stock pot, or if you're doing like a crab boil, it takes a lot more energy to get that water boiling. So the mass of whatever it is that you are trying to increase its temperature is one of the big dependent forces. The other one is the change in temperature. How much energy do you have to change to get it to boil? So water, you have to get it from whatever the temperature it is to 100 degrees Celsius or 212 Fahrenheit. So that change in temperature there. So the bigger the temperature change, obviously, the more heat you have to add. And then the last thing, or the last variable in this equation, C, that's the phase of the substance. And this is known as the specific heat. So the specific heat is dependent on the material. So different materials are going to take a different amount of energy to increase their temperatures. Something like brick is going to take a lot longer to heat up than something like copper. If you've ever soldered copper pipe, you know that you solder it with a torch for a couple seconds and the pipe gets really hot really fast. Whereas if you take that same torch and put it on a brick wall, right, you can keep it on there for a minute or two, pull the torch away and touch the brick with your hand, it wouldn't be that hot. Because brick has a much higher specific heat than copper. It takes more energy to change the temperature. Likewise, the copper cools down fairly quickly, whereas the brick is going to take a lot longer to cool down. On the right, that's a water bottle, a hot water bottle. These are used when you're sick. If you ever had the flu or anything and you get the shivers, your mom or grandma or somebody may give you a hot water bottle, so they fill that up with hot water. You hold on to that and it keeps you warm. Water has a very high specific heat. Water, if you've ever noticed, like if you boiled hard-boiled eggs on the stove, if you boil the water and then you take the eggs out and you move the water off the burner and you come back in like an hour and touch the water, it's still warm. That's because water has a high specific heat. This is what allows us to take a bath for a long period of time. Right? If water had a low specific heat, you'd fill up the bathtub and the water would be cold instantaneously. But because water has a high specific heat, it keeps its temperature. It makes things a lot more comfortable. As you add as you add heat and increase the temperature, objects go through phase changes. So we'll start with a solid and we'll go through this cycle here. If you take a solid and you add energy, you can see it going up here, the red. If you add energy, the solid melts and becomes a liquid. If you continue adding energy here in the red, it's going to be vaporized. So you're going to take a liquid, you're going to turn it into a gas. Between a solid and a liquid, that temperature where it turns from a solid to a liquid is called the melting point. And between a liquid and a gas, that temperature that changes it from a liquid to a gas is called the boiling point. It also happens in the opposite direction. If you take energy out of a gas, the gas condenses and turns into a liquid. If you take a liquid and you take energy out of the liquid, it turns into a solid. So when you're pulling energy out, it condenses. And when you're pulling energy out, it freezes. If you think about a window in the winter time, or in the fall and the spring or the summer especially, the window can get condensation on it. This is due to the difference in temperature from the outside air and the inside air. If the inside air is a lot cooler than the outside air, sometimes your windows will, and it's very humid, your windows will fog up because it's trying that glass is trying to get to the same temperature on the inside and the outside. So what happens is that high energy on the outside is trying to get inside. It causes that water inside to condense on the window to get them to that same temperature. So it takes that water vapor. Sometimes they put a barrier of nitrogen in the window between the double pane window glasses, and that will help cut down condensation. It won't have as much energy being transferred between. So condensation, we call that a warming process. So if inside your house where your air conditioner's on, it's cold, outside it's hot, so it's trying to warm up or take energy out the inside air, and that's what causes that condensation. Vaporization is a cooling process. If you have ever been in a pool and you get out of the pool in the summertime, all that water vapor or all that water on your body vaporizes very quickly. It evaporates off of your skin and it kind of cools you down. Like when you're in the shower and you're just turn the shower off, you're still warm, but as soon as you open that shower curtain, you get cold. That's because the water that's been condensed on your skin is now vaporizing away and it's cooling you down. The final phase change is going directly from a solid to a gas. That's sublimation. And then going opposite, gas directly to a solid. That's called deposition. Here we can look at the melting. The melting changes from a solid to a liquid. Energy is added to the system. And then freezing. Freezing is going from a liquid to a solid, and we're taking energy away from the system. Likewise with evaporation. Evaporation is changing from a liquid to a gas. We're adding energy. And then condensation is changing from a gas to a liquid, and energy is taken out of the system. Sublimation is changing from a solid to a gas. Frost on your windows in the morning is a good example of sublimation, right? You turn your heater on in your car, and that solid goes directly to vapor. It doesn't. A lot of it doesn't melt away. Here you can see dry ice. Dry ice is pretty famous for being something that goes through the sublimation process. Heat flows between objects in three manners: conduction, convection, and radiation. These are the three ways for heat to flow. Heat always flows from hot to cold. We'll learn more about this when we talk about thermodynamics, but we're always going from hot to cold. Our picture over here shows three ways that fire is going to transfer heat. The fire has more temperature than the hands in all three cases. The first one we'll look at is conduction. So if he sticks that metal poker in the fire, the metal poker is going to get hot, and the atoms are going to collide with each other and transfer up to his hands. The next one, convection. Convection is the transfer of heat through currents in a fluid. So the fluid is the air. So as it goes through the air, it gets between the fire and the hands. And then the third one would be radiation. The fire isn't going to send out heat. It heats above, it goes above. So the radiation is actually the heat from the flames going to the hands there. So if you ever had a fire in your house, you got these three things going on. Convection, that would be the heat. If you turn the blowers on your fire, it blows the hot air out. That's your convection. Radiation is if you sit in front of the fire. Like when I was a kid, we would sit in front of the fire, my brother and I, see who could sit there the longest and withstand the heat from the radiation from the flames. And then the third one is conduction. If you stick something in a fire, like if you're making s'mores and you stick your metal rod in the fire, the rod is going to conduct heat through there and to your hand. So let's take a look at those in more detail. Conduction. Conduction occurs because, as you can see in this picture, let's just assume that's a metal rod. That flame is heating the atoms closest to it. Those atoms inside the rod are moving and colliding with each other. So as it moves, the energy goes from one atom to the next right on down the rod until it gets to the end of the rod. This is how conduction works. It's the transfer of heat through materials in contact with each other. Convection works through buoyant forces. So hot air we know rises and cold air falls. So this is a little convection oven over here. And as it gets heated on the bottom, the hot air rises up to the top of the oven, then it replaces, or the colder air at the top of the oven falls and replaces the hot air, and then you move the air around with a fan and to help heat completely, and that's how a convection oven works. This is also how the hot water heater in your house works. the heating filaments at the bottom of the hot water heater. So you pipe in the cold water is in your tank, you heat it up, the hot water rises to the top of the tank, the cold water falls and replaces the hot water, and it creates a convection current in your hot water heater. The third way is radiation. This is how your microwave oven heats something. It sends out microwaves, and the microwaves collide with molecules in the food, mainly water molecules, and they increase the kinetic energy of the water molecules. And as you increase that kinetic energy, it causes it to cook your food, so to speak. So radiation is waves that are absorbed or emitted. Well, essentially, if you're going to heat something, you're going to emit them, and then also the waves get absorbed by things. And the absorption is what causes the temperature of the new object to arise. And the way that they're emitted is through inside the atoms. When the electrons change orbits, they give off radioactive waves. Or not, excuse me, not radioactive, electromagnetic waves. And those electromagnetic waves are going to have certain energy levels based on how far that electron moved in its orbit. So the long story short is objects that are in high energy states fall to low energy states, and when they fall, they emit electromagnetic waves, and those waves then are absorbed by materials, and that's what causes those materials to gain temperature. There are a few different types of electromagnetic waves. These waves are going to go, in the picture below, they go from low frequency, low energy waves to high energy waves. So things like microwave, infrared, visible, those are low frequency, low energy waves. X-rays, gamma rays, those are high energy waves. So the more energetic the wave is, the more heat it's going to be able to transfer, the higher the temperature is going to get. So it's just something we're going to look in greater detail about as we move forward, but for now we're just introducing it. Just need to remember that the higher the energy level, that relates directly to the frequency. And one more look at the electromagnetic spectrum. You can see the size of the waves here. Radio waves have very low energy, low frequency. The wavelength then would be a much bigger, because remember, the wavelength and the frequency are going to be inversely related, because all electromagnetic waves travel at the speed of light. So if the frequency is low, that means the wavelength is big. So radio waves are relatively large, or the biggest, and then you can see over there on the right, the gamma rays are really going to be tiny waves, 10 to the minus 12th, that's their wavelength, that's really small. But they have a tremendous amount of frequency, and those would be like your nuclear waves and things like that, radioactive waves, things that you would think of if you watch science fiction, right? That's the Spider-Man, Incredible Hulk, things that are going to do permanent damage to you. So that is a little bit about heat transfer.